All right, we've been looking at inequalities and solving multiple step inequalities and some unique situations that happen. We're going to spend a little bit more time today looking at some real world situations because, again, we have to be able to deal with the real world when it happens. And so a big part of real world situations are what are called compound inequalities, because sometimes you want to be less than one number but greater than another. I want to find that sweet spot, right? You want to be not too hot, not too cold, just right. So we're going to be looking at what happens when things are not too hot, but not too cold, and they're just right in that sweet spot. The age of students in this class, and this is pretty accurate, I would assume, are between 11 and 13, inclusive. Write a compound inequality to show those ages of the students in this class. So let's see. If you are a student, we're going to go with S in this class. Your S is probably going to be better than mine, but there you go. If you are a student in this class, you are going to be less than 13 years old, or exactly 13 years old, right? You could be 13 and be in this class. I guess I'm not positive as to how old the students are in here. I would assume that somebody could be 13 years old. So you could be 13 and be a 7th grader. But you could also be less than 13. You could be 12. All right, we have a lot of 12-year-olds in this class. And so you could be less than 13. But we don't have any 2-year-olds in the class because 2 is less than or equal to 13. So 2 could be an answer at this point. So S could also be, or should also be, greater than 11. However, you could be younger. You could be 11 and be in this class. So you could be 11 or older, and you could be 13 or younger. And the way we put these two inequalities together is we say that S is in between 13 and 11 years old. And in math, the word between has a couple different meanings, but in this case, we're going to say that S is greater than or equal to 11, and S is less than or equal to 13. And so a compound inequality means that we have two different inequalities together, and that gives us some bounds, so a range of values that will work between 11 and 13. And this word inclusive means we're going to include 11 and 13. Exclusive is like you're excluding people from your club. 11 and 13 would not be included, so an exclusive club would be not including 13 and 11, which would really just be like 12 or 12 and a half or 11 and a half. So we wouldn't be including that. That would be exclusive. But an inclusive club means we are including people. We're being really nice. We're going to include 11 and 12 in this particular group. And now we're going to graph it. Okay, so graphing a compound inequality might have a few more numbers on it. We need to have 11 on there, and we need to have 13 on there, because those are two numbers that are on my number line. We have two solutions. And then we're going to put a couple numbers on either side. And so we've got our graph. It's a little bit longer, but it has to include both of those numbers. Now, we can graph these numbers. So what is a value that S could be? Well, S could be 12. S could be 11 and a half. S could be 12 and a half. X could be 12 and a third. 11 and 3/4. Could be exactly 11. Could be 13. Could it be 14? Could you be 14 and be in this class, according to our inequality here? No. No, 14 does not work. Between 11 and 13. 10. No, 10 would not work because, again, that's too young. We said you have to be between 11 and 13. But really, anything in between here would be okay. And that kind of looks like a line. Hey, there we go. And since we are including 11 and we are including 13, we have our inequality. We've graphed it. It's between 11 and 13, every single number in between 11 and 13, including 13 and 11. And there's our graph. So let's another one. Oh, I apologize. Here's the general synopsis. We're going to be concentrating in this session in these notes on the and here, which is what we were just talking about. That we've got an inclusive. Inclusive is looking at these ones here. We're including 2 and 6. And an exclusive means that we're not including 2 and 6. And you can see that in the graphs, that 2 and 6 are not included in that exclusive inequality. And in the second one here, 2 and 6 are included. That would be that inclusive compound inequality. Or we are going to look at the or ones, but I think those are going to be in a separate video. And so we're going to concentrate on the and ones in this particular video. Okay, pH. pH is like acid or base, how acidic things are. So the pH level of a popular shampoo is between 6 and 6.5 inclusive. So again, that's you don't want your the shampoo to have so much acid in it that it burns your scalp. That would be bad. So we've got this sweet spot between 6 and 6.5 for a popular shampoo product. So we're going to make a compound inequality and graph it. So if the pH level, we'll go with, I don't know, X, is between 6 and 6.5. So here's 6, here's 6.5. If it's in between and it is inclusive, so we are including 6, and we are including 6.5. So X is greater than or equal to 6, but X is less than or equal to 6.5. Now be careful, you cannot, I'm going to put this in blue over here, you cannot do it this way. My marker will work, here we go. You cannot set it up that way because this would say that X is less than 6, but X is more than 6.5. That can't happen. There is no number that is less than 6 and more than 6.5. That does not exist. So this would be a wrong way of writing that inequality. You have to be very careful of the order that you put those numbers. You could not say that X is less than or equal to 6 and greater than or equal to 6.5 like this. Again, there is no number that's greater than 6, but also, well, I guess I take that back. There is a ton of numbers that are greater than 6 and greater than 6.5, but at that point, you really don't need this first part here, because any number greater than 6.5 is also going to be greater than 6.0, and so that would be redundant. And really what you need to be careful of, what you want to remember, is that the inequalities should not be pointing at each other. They should be going in the same direction. Okay, so that would also be an incorrect way of writing it. But we've got our inequality here, that X is in between 6 and 6.5 inclusive. We're going to graph that. So again, I need to have 6, and I need to have 6.5. So I might go 6.0, 6.1, 6.2, 6.3, 6.4, and 6.5. Might need to have a couple numbers on there. Go with maybe 5.9 here, just to fill it out. So if I'm going to graph that, I'm including 6, I'm including 6.5, and X is in between, which means not this way. That way is not in between, but in between those two dots. Everything in between would be acceptable for this shampoo. And that's our graph. So yes, you do need to have a bunch of numbers on there. We couldn't count by 2s because that wouldn't work. So I counted by 0.1s, by 6.1, 2, 3, 4, 5. But you got to get them all in there, and you can't count by 6, 6.5. It's not a very big range. We need to have a little bit more of a range in our graph. So get another one. So if you want to, go ahead and pause it, try it on your own now that you kind of see how these are set up. But if you paused it, you tried it on your own, you can see how I'm going to do it and match up with what you did compared to with what I do. Free chlorine in a pool. So you've been to a swimming pool. You don't have too much chlorine. It burns your eyes. You don't have too little chlorine. It won't kill the pee that people put in the pool. Gross. And so we want to have that sweet spot that is in between, that is between 1 and 3 parts per million. So if you took 1,000,000 parts of water, one of those parts would be chlorine, or between that or 3 parts of chlorine. So X is in between, and we are inclusive in this. So we're going to include 3, we're going to include 1. We're going to graph that then. Now for this one, I can go 1 and 2 and 3, because there is something in between. So I can make my graph a little bit smaller in this case. I don't need to count by tenths. We'd have just 0, I guess, here. And I'm going to include 1. I'm going to include 3, and everything in between. And now I have my inequality. Because again, 0 wouldn't work, so we can't have the line go this way. And 4 wouldn't work, because we can't have the line go that way. So everything in between 1 and 3. There's no arrows for this, because we can't include bigger numbers or smaller numbers, just in between. Okay, solving a compound inequality. Now sometimes you'll see an inequality that looks like this, and we have to get x by itself. We can't graph it at this point because we don't know what x is. We don't have a bound for x because of that plus 1. So what we're going to do is we're going to solve this inequality twice. We're going to look at the right side first, just because. So we're going to look at the right side first. X plus 1 is less than 2. I don't care about the other part. I just know that x plus 1 is less than 2. So I'm going to solve this. Do the inverse operation. I'm going to subtract 1 from both sides. I'm going to get that x is less than 1. Now, I'm going to look at the left side of the inequality. I see that x plus 1 is greater than negative 5. So if I do the inequality, I'm going to minus 1 from both sides here. And I'm going to get that x is greater than negative 6. I have an inequality. Now, this is an exclusive club. X cannot be 1 and x cannot be negative 6, but x is in between negative 6 and 1. So if we pick any number between negative 6 and 1, how about 0? 0 is between negative 6 and 1. If I substitute 0 back in, 0 plus 1, well, 0 plus 1 is 1, and 1 is in between 2 and negative 5. So it works. So if you pick any number in between negative 6 and 1, you will have a solution to that original inequality. Get rid of what I have up here. Now we're going to graph it. And so we've got a graph between negative 6 and 1. So I've got negative 6, 5, 4, 3, 2, 1, 0. So here's 1, 0. I go negative 2, 4, just so that I don't get all crammed in there with numbers. 2, there we go. And so I've got enough dashes. I did count in an okay timeline there. I just didn't fill in every single number to save space. Between negative 6 and 1. Now again, I'm not including negative 6 here. This is an exclusive club, an exclusive graph. So I'm not including negative 6. I'm not including negative 1. But I am going to include everything in between. And there we go. We've graphed a compound inequality. We've solved it by solving it twice, essentially. We covered up one side and solved, covered up the other side and solved, and we got our final answer. Another one down here. Oh, hey, here we go. So graphing solutions, you can think about it as putting the two different lines together here. And so they're overlapping. And that's another way to look at it, is that overlap. Is it's less than 10 with this one. It's greater than 0 with this one. And since it's in between, where do those cut off? And you can kind of see it there. So if my explanation before wasn't enough, you can look at this example as well as another way of explaining how we get that graph. Okay. So solving the compound inequalities. Pause it. See if you can get these two on your own. Make sure you graph. Okay, let's see how we do here. So I'm going to solve the inequality. I'm going to do the inverse operation. It says x minus 10. So I'm going to add 10. I have to do that once to the right and once to the left, because it's two different inequalities that I'm doing at the exact same time. Okay, so I've got x in the middle. Negative 5 plus 10 is 5. And negative 9 plus 10 is 1. X is in between. Any number between 1 and 5 will work for that original inequality. I'm going to graph my solutions. So I've got 1 and 5. So 0, 1, 2, 3, 4, 5, 6. 5, 3, 1. There we go. And so I've got my inequality. I am not including 1, and I am not including 5. We have an exclusive arrangement. and everything in between. Bottom one. Again, I'm solving two inequalities at the same time. I've got 3n plus 5. I go backwards through PEMDAS. I do my Snoit to repo for redrow. The inverse operation, the opposite of plus, is minus 5. I'm going to minus 5 from all sides now, because I've got more than just two sides. 11 minus 5 is going to give me 6. 3n is still there. Have not done anything with the 3n yet. So the 3n is still there. And negative 4 minus 5, negative 9. N is still not by itself. I do the inverse operation. I divide everything by 3. There we go. It's a positive 3, so I don't have to worry about flipping any signs around. I've got n, and 6 divided by 3 is 2. Negative 9 divided by 3 is negative 3. And I have an inequality. Any number n between negative 3 and 2 will work in the original inequality. And I'll let you test that for yourself if you want. I'm going to graph it. So I need negative 3 on there. I need 2 on there. So I need 4, 3, 2, 1, 0. 1, 2, 3. Okay. 1, 2, negative 3, negative 4. And if I'm going to graph it, now I'm including negative 3 here. I'm going to use a different color. I'm including negative 3. Negative 3 is inclusive. I have n is greater than or equal to negative 3. But 2 is not included. N is less than 2, but not equal to 2. So I have an inclusive and an exclusive. We like some people, but not others. And so we are including negative 3, but we are not including 2. They didn't give you a good birthday present. They're not included. And so we've got our inclusive and exclusive graph there, and we can plot those points. Okay, this is going to take some practice. We're going to spend a couple days on this. What I want you to do is maybe try this one on your own. Same kind of idea, but give this one a try on your own. And then page 207, 30 through 34. I did not print them out this time, but you can look in the book or the online book to get those questions.